Thank you for the intro. Yes, Georgios, I guess you can hear me and you can see the slides. I assume that's correct. And today I will give an introduction about e-commerce at Meta and how we use machine learning and deep learning in particular for providing recommendations for e-commerce. So the talk is going to be pretty high level. So even if you're not familiar with the fields of machine learning and recommender systems, you should be able to follow most of it. So let's start. Let's see slides. Yeah, okay. I assume the slides changed and they're working fine. So yeah, this is how the product looks in a nutshell. So Facebook and Instagram shops have been launched relatively recently in May 2020. And this is a glimpse of how the user experience looks like. So you have, as in many e-commerce platforms, users that interact with various shops, and the shops have various products, and the users can interact with these products and purchase them either on site, so on the platform provided by Meta, which is Instagram or Facebook in particular, or they can be purchased off-site, so there can be a link to an external website where the users can go and buy the item. And one important aspect of such a platform, which again bears a lot of commonalities with existing e-commerce platforms, is that you have multiple surfaces where the user is recommended certain items. And these surfaces depend on where exactly the user is at browsing the app, the product. So a user can be, for example, when you just open the application, you have a set of recommendations that are personalized and are quite diverse. And this we can call this products for you in surface. If the user clicks on a particular shop, then typically recommendations are from the same shop, maybe different items, and this is the more from the shop surface example. Another example is if you click on a product, then you might get a section where you have recommendations for similar items to this product, and so on and so forth. And as you can imagine, each of these services calls for different solutions in terms of both the system side and the algorithm side in order to provide relevant recommendations. So to discuss a bit more and to get into how we use machine learning to perform recommendation under these surfaces, let's take a step back and sort of give an overview of what the recommendation system is. So you have a database of users that contain their actions in the short and long term. And you have another database of the items. And then you put those into a ranking system that outputs a set of items or products that are likely to be engaged by the user. Now, taking a step forward towards understanding how machine learning is thrown into the mix, let's consider the sort of standard scheme for recommendation with machine learning. It's sort of the textbooks solution. Here we have a use case, which is particularly easy, and I will explain why it's easy later on. But let's go through it in more detail. So we have the goal of recommending movies to users, and the particularity which makes the task easy is that users give explicit ratings to those movies. And these ratings, they can be seen as a database where on the rows you have the users, and on the columns, you have the products. And here, for example, in the first row, you can see the user gave 10 to the Godfather, did not rate. That's why we have the -1 to the Inception, gave 8 rating to Leon, and so on and so forth for the rest of the users and the rest of the products. Okay, so what is the technique? The technique is called matrix factorization. And what we want to do here is essentially create a representation of each user and each item separately. And how we do that, we get the initial matrix, which consists of all the user feedback, all these ratings, and we try to approximate it with 2 other matrices, the inner product of 2 other matrices, a user matrix and an item matrix. So in this way, each user, each row will have a separate vector, and each item will have a separate vector with a dimension that we set as a parameter. And at this point here, it's marked as 3, but we can increase it if we want larger capacity for our model. So this is a hyperparameter for a model. So what we essentially do is take these users and these products, and we create a mathematical representation that puts them in the same space, in the same hyperspace. And then we can do all sorts of things with these representations, compare them, and so on. So how do we do this? How do we ensure this accurate representation? Well, we have multiple tools which have been well established and developed over the years for doing that. And essentially, we start with let's say, a random assignment of values on the user and item matrix. And then we follow an iterative procedure towards some optimization goal that in this case is to predict existing ratings accurately. So coming back to the example, not sure if you can see my mouse, but you can imagine the first row of the user matrix multiplied inner product with the first column of the item matrix will give you the estimation for the first element, which is 10. If the estimation is, given the initial values, 5, then this means that there needs to be some updates to certain parameters to this representation. And this update needs to be towards increasing this rating. So this is the rationale behind the main optimization scheme, the most popular one, which is called stochastic gradient descent. And this scheme has a tremendous amount of variants. It's dedicated to different use cases and different problems and different setups of training a machine learning model. But we'll not go through details of this algorithm. So essentially what this algorithm does is take multiple steps, as I mentioned before, and essentially reach a point where we know that the representation is either accurate enough or as accurate as can be, depending on whereas the problem we are tackling is convex or not. And at that point, we can assume that we have an accurate representation of a user and an item. At the final step, we use this representation to make predictions for the unrated items. So we use this representation to say, oh, how much would the first user rate Inception? That would be an 8. And how much the second user would rate Pulp Fiction? That would be an 8, and so on and so forth. So after we do these predictions on the final step, we use them to provide the recommendations. So to do the actual ranking. This is a slightly different, let's say, database, but the takeaway is the same. So you have a user, and then the predictions are the following. So if you would like to give, let's say, the top 2 most recommended movies for this user, you would select Batman and Spider-Man. And in the second one, you would select, I guess this is something like Avengers, and then Spider-Man, and so on and so forth. So at this step, I would like to come back to what I mentioned before. regarding the previously the example that I just explained with the movies predictions as a relatively simple task, and illustrate some of the main challenges we have at Meta for recommendations. So the first and foremost is that we don't have this very useful information of explicit user feedback. In the case of movie ratings, the user gives explicit knowledge to the system as to his or her preferences by rating movies to a scale of 0 to 10. So you can infer all sorts of stuff by just two, ratings. The user rated Inception with an 8, and then it rated, I don't know, Harry Potter with a 5. So taking into consideration what is the average predictions for these ratings, you can understand the taste of the user, the related preference among the two movies, and so on. But for the case of an e-commerce platform, such as Facebook and Instagram shops, we don't have this feedback. What we do have instead is some interaction events between user and items, such as user clicking on items, or more rarely user liking some item, or user buying some item, or putting the item to a wish list. And as you can imagine, this doesn't necessarily, like a user clicking an item doesn't necessarily mean that the user really likes the item. So recommendation in this regime is significantly more challenging. The second part is the scale, which is quite common quite a common challenge in Meta, given the number of users and items. And this creates challenges in turn for both the system design, how to actually implement the model training and the model inference or surveying, as we call it, so using the model to make predictions, and at the same time guarantee a good user behavior in terms of responsiveness and quality. So have a robust platform that serves many users and items. So it creates a lot of challenges on the implementation side, on the system design side, but it also creates a lot of challenges on the algorithmic perspective. And this is where a lot of people working in theory of computer science, they come together to create better solutions. For example, some better variant of the stochastic gradient descent algorithm that I described before, that is suitable to train on multiple machines and operate into the scale of multiple, like a lot of users and items. And the third part is another reason why the problem I mentioned before about movie recommendations is easier, is the user dynamics. So we actually worked on a paper in the beginning of my PhD where we showed that even for a well-established database regarding movie recommendations, you can observe that the user behavior drifts. So as time goes by, users tend to change what they prefer and like. And we showed that for movies. So you can imagine to what extent this is happening for a platform where users go and buy products. And therefore there is no state that you can safely say and assume that you really know what the user has on his or her mind and what she or he is up to. So with this in mind, again, the nutshell representation of a recommendation can be revisited, and we revisit it in the following way. So we have a very large database of user actions, a very large corpus of these actions. And we have a very large corpus of items and products. And therefore, we need to sample these products through a phase that we call the retrieval, which itself is using machine learning. And from this phase, we have a significantly smaller set of candidate items that are sent afterwards to the ranking phase, where the final set of top 5 or 8 recommendations is given to the user. And of course, as I mentioned this in the beginning, this whole setup needs to be sort of not repeated, but tailored to the recommendation surface. Remember the beginning of the presentation where we discussed about more from the shops, similar items, and so on and so forth. Now, how does the deep part falls into the mix, and how do we essentially use machine learning to drive these recommendations? Again, this is a high-level description of the situation. So in the initial part, we take these users and items, and we extract certain features from them. These features can be dense, continuous, such as the user height, for example, or they can be sparse, categorical, such as the item count. Then we take these features and we extract a representation similar to what we did in the example that I showed before regarding movie recommendations. We call these representations embeddings. This is a term that you might have seen in machine learning. And essentially, what we do with this representation is feed them to some neural networks, which are called multi-layer perceptrons. And we repeat this procedure into multiple levels. So we use the output of these neural networks to create a higher level representation, which we then feed to other networks and so on and so forth. And essentially we reach stage 5, where we have a way to predict whether a user will engage with a certain item. And this is essentially a score or a measurement of affinity between a user and an item, similar to, in our example, this rating prediction. And based on this score, so these scores are comparable among items, we rank them, and then we select the top 5 or top 4 most likely to be engaged items. And at this point, I would like to highlight some of the bottlenecks that lie in different stages of this procedure. So for the feature extraction part, there is a lot of storage requirements. It would be great to have everything in flash memory and be able to use them super fast, but this is infeasible in practice. So there needs to be some trade-offs depending on the type of the feature and how frequently it's updated and so on. The second part about the embeddings lookup is the bottleneck there is the memory bandwidth. So we require multiple fetches of this information to be able to compute these higher level representation and the interactions between the embeddings. For the interactions, there is a lot of movement of data across different machines. So the networking is the bottleneck here, and at the top of the architecture, we have significant compute requirements, which are satisfied by mostly GPUs, but also CPUs. And I would like to conclude this high-level presentation by highlighting some of the challenges that I personally think are important and are currently we are investing a lot to as a company. And I have seen a lot of work while I was in academia on this. So again, these are some keywords. So a lot of these areas have overlap. And so we have distributed training. So how can we use multiple machines to have larger models trained on much faster and much more frequently, so they can capture more short-term behavior of the user. recall that we have the problem of behavior drift. So this is very important for our case of e-commerce recommendations. Then we have the option to parallelize the data processing, and at the same time, the option to parallelize the model processing. So how can we play around with these sort of parallelisms? Then on the third part, we have the option to update the state of the model or the parameters of a model in a synchronous way, again, when deployed in multiple machines, or in an asynchronous way, meaning that we can essentially play with the trade-off between, you have a more stale and maybe a bit of inconsistent results in your model parameters in the updates, but you can do them faster versus wait, do things synchronously, have the right state, but be slower. And depending on the application and on the modeling architecture, each choice has its pros and cons. So the fourth part, again, with respect to distributed training, do we want to keep all the model state in a single place, centralized, which is often called a parameter server, or do we want to use a more, let's say, decentralized approach where the state is hold, like multiple machines hold the state, such as the old reduced architecture. Then we have online training, which I briefly mentioned is very important to capture this user behavior drifting. And last but by no means least is how can we ensure the user's privacy while at the same time taking into consideration behavior that is important and very, very helpful for providing relevant recommendations. And with this note, I would like to thank you for attending this presentation. And I would be happy to hear any questions or comments that you have. And feel free to reach out in the website. All the information there is